Let me introduce you is Philippe Strasberg. He's in Universidad Autónoma de Barcelona right now as a junior leader in IFCA foundation grant. He did his PhD in Berlin, in the Technical University, then went to Luxembourg for postdoc, and then Barcelona. He's been in Spain 5 years, but for this talk, I think he prefers to speak in English for obvious reasons. And he's been working on thermodynamic of quantum open systems or thermodynamics of open systems from mostly a quantum perspective. He has experience in stochastic processes and statistical mechanics, classical and quantum. I think he brings this title to catch the attention of people, but I think you will explain better. Everything, everywhere, all at once. So,
right.
Go on.
Okay. Yeah, thank you very much and welcome. Can you all hear me? Is this fine? So yeah, my name is Philip, and well, I'm here a little bit to explore possibilities for Remarkably as well. I mean, I think the final result is not yet out, but so far I was shortlisted there. And as one said, I would describe myself as somebody with a background in statistical physics and stochastic processes, mostly on the quantum and non-equilibrium side. So you might wonder, what the heck can I tell you about the many worlds interpretation of quantum mechanics? Actually, my main goal is to convince you that I can tell you quite a lot. And there's actually a lot of stuff in the background, although I'm not emphasizing it too much. And in my view, there really is a lot open we need to understand before we can actually start talking about the many worlds interpretation on any serious level. So before I start, let me just say there were some co-workers during the initial phase. I worked together with Jochen Gemmer and Josie Wang from Osnabrück and Andreas Winter from Barcelona. But actually, I will mostly talk about recent results that I got with Teresa Reiner and Zoe Schindler from Barcelona. All right. So, that doesn't work. That way. So what's the outline of this talk? Well, I'll very briefly try to review what is the many worlds interpretation. And I will introduce a formalism of, say, histories, which I use to address this problem theoretically, or talk about many worlds. And then I come to the two main problems for the acceptance of, say, of the many worlds interpretation. I will explain them in due time, and then I conclude. Okay, so that's a strategy for today. So what's the many worlds interpretation? I will only talk about non-relativistic quantum mechanics today for simplicity. And then what it says is, well, there's one big isolated system, let's say the universe, if you want to call it like that. That's described by some Hamiltonian H, and there's a wave function for it. And that's it, okay? So there's really nothing else, and what many worlds promises that you can make sense of quantum mechanics and everything based only on these two things. Okay, and I think for these reasons, it attracts attention, basically because it promises a very okay, gracias, thank you. Because it promises a very simple account of quantum mechanics. Okay, arguably maybe the simplest way to make sense of it. Well, but we all know that one kind of interesting well, I'm fine with that. There's one consequence, and well, hopefully I don't have to go through all the details. You all know Schrödinger's cat, the famous thought experiment. What can happen is that if you have a small quantum system and that is in some superposition, And if that couples to some, say, macroscopic system, then at the end of the day, that macroscopic system will also be in a superposition, like Schrödinger's cat being dead and alive, and you end up with a wave function where different components will describe macroscopically distinct physical situations, like a cat which is dead and alive, and an observer with either the cat being dead or alive, and so on and so forth. So, oops. So the first point I want to make, and I think because this is not always well presented, the multiverse is really a prediction of the many-verse interpretation, not a postulate, right? It's not that we say, there are these multiverses, and that's what we postulate, but no, this comes out just by linearity or unitarity of the time evolution in quantum mechanics. Okay. Now, how to address these kind of different worlds a little bit better? Well, to this end, I will introduce a technique which I will use throughout the talk. So I will try to go through it slowly, which is known as the histories formalism, and which got quite a bit of attention in the 80s, 90s, and early 2000s. And well, what do I mean by that? So let's start at T0. You have some initial wave function of your full isolated system of your universe, right? And you want to ask certain questions about it, about certain physical properties. And as usual, we address them in quantum mechanics with a complete set of orthogonal projectors, right? And those projectors, they project on different properties, could be spin up or down, but they're completely arbitrary here. And they basically divide your Hilbert space into subspaces compatible with different physical properties. So what I do is I multiply that state with these projectors and sum over all these projectors, okay? And because the complete set of projectors, the sum over all projectors is just the identity matrix, all right? That's very important. So I'm just multiplying my identity. There's no collapse of the wave function. I don't change the state. It's basically something trivial, all right? So this I do at time t0, and then I let evolve the time at a state evolve in time, just Hamiltonian unitary dynamics from the Schrödinger equation. And then I do the same again. So at time t1, I insert this identity as a sum over all these projectors, and I try to sketch this here. So this is my Hilbert space, and I divide it up into different subspaces here labeled 1 to 5. And I continue with unitary evolution, and again insert a projector, and so on and so forth. All right. Then at the end, what you have, well, you can take all these summation symbols and put them to the left, right? And then what you basically end up with is a decomposition of that state in such a form where I use a bold space X to denote all these labels here at all these different times, okay? And psi condition on X is everything except for the summation symbol, so basically all these terms here, this entire string of terms, all right? And this X, I will also call the history, and this could be then called a branch in your multiverse, all right? So if you think about it, it looks like a path integral simply, okay? I hope you have seen the path integral in quantum mechanics. Indeed, if I, take the time difference going to 0, and if I would use as my basis a position basis, this literally becomes a Feynman path integral, right? Here it's just more general. I take arbitrary times and so far just some arbitrary projectors, okay? That's a way to just figure out how the state basically evolves through your Hilbert space. Is there any question on that? Because I will use that formalism. I hope it kind of makes sense. What's everyone? Does it make sense? Kind of, maybe. Right? I mean, for instance, here, these colorful things are specific examples of this kind of thing, right? So here is you are localized to the partition 3 at time 0, that's by 3 subscript 0. you continue here at time T1, you're still in 3, but at T2, you're in 4, and that's the way it would go, right? It's just splitting up the component of your wave function. Right? Okay.
Sorry,
Yes, please.
you say there was a condition on the sum of the projector.
Yeah, so they always add up to the identity. So this is just an identity matrix. So I'm really not changing the state. So you can actually really also, you can take these things out, and then you just get unitary time resolution and you have your final state just propagated forward.
So the sum of over x of pi x of all of them is 1. Is identical.
Yeah, so the sum of x pi x is 1, the identity matrix. Yeah. That's basically the standard thing that you get. Any observable you're interested in its eigenbasis, right? It has all the eigenvectors or the eigenprojectors in that sense. And they always span the entire Hilbert space. So if you sum over all of them, you get an identity. So it's just saying I have all possible options here somehow in some basis, like spin up, spin down in that direction, or the position basis, or anything. Yeah.
In the last identity, you are calling or rephrasing your state at time Tn, like this sum of all these intermediate points, but then you are discretizing your space. So, in a certain, is there any criterion for that? So you make
No, so far not, yeah. So basically there's a double discretization, right? One in time, which you choose, and actually I think the n should be the L actually here. I'm just realizing that, in case you are confused. And then, I mean, this does not need to be physical space. This is abstract Hilbert space. And, whatever kind of question you ask about a quantum system can be described by some projector, and the projector just splits up your Hilbert space into non-overlapping subspaces, right? So, like cat is dead or is alive or all. And so far it's completely general here. There's nothing particular. All right. So I hope you don't feel too uncomfortable with that. So I want to talk about the first problem, which is related to the many-modes interpretation, and that's known as the preferred basis problem. What does it mean? Well, I hope you have the same sensations as I do, and I think I live in a classical world. I don't see Schrödinger's cats around me. I don't have any kind of weird quantum interference or measurement back action. Everything looks quite classical. And the question simply is, okay, how can it be that our perception of the world is classical, and which kind of basis or coarse graining or what kind of projectors actually generate such a classical world? All right. And I think there are many important detailed questions still open, but I guess also there's no doubt that more or less the general answer to this problem is decoherence, right? So that actually a coherent superposition in a wave function can behave classically, so it can lose phase coherence. Now, typically the way decoherence, the standard story is via some system Barth division, and you talk about the open system, how it loses coherence. I will actually present here a more like StatMech inspired perspective, which I think is interesting in its own right and does not contradict decoherence in open quantum systems, but has some different features. Okay. So let me start with what decoherence means for these kind of histories going through Hilbert space. Okay. And yeah, before I just explain the mathematics, just let me make one remark. There are, of course, many different features how you can distinguish quantum from classical mechanics. And I'm just saying this is one way to do it, and it's not the only way to do it. And I will try to justify why it's a good way in a minute. But I want to make this clear that I'm not claiming this is the only way to talk about the quantum to classical transition. So I hope you remember we had these states that were conditioned on passing through some trajectory or phase in your Hilbert state. And what you say is like, you take two states, you take the inner product, the overlap, and you want to have this much smaller than basically the norms of each state, okay, for different trajectories. Why do you want this? Well, actually, by something called Cauchy-Schwarz inequality, you can always put that this object is smaller than that product, so you want to have it much, much, much smaller to have something like decoherence. Now, why does this have anything to do with decoherence? Well, let me make the following comparison. So remember what coherence or interference means for a single time quantum state. So suppose we have a state which is a coherent superposition of two different states, and you ask some question about some property described by pi subscript x. So that's the probability. So now if you insert this state, you get 4 terms at the end, right? And you get these diagonal terms like pi 1, pi x, pi 1, which is this term, and the other diagonal term, and then you get these cross terms, right? And typically people say, well, that's classical, there's quantum interference. Why? Well, because if we would take this state and actually replace the coherent superposition by a statistical ensemble, like a mixture of these two states, then these two states would, or these two terms would vanish and they would remain unchanged. Okay. So basically, what this condition says is basically, this idea applied just to this multi-time history, right? That you can basically, let me go back, take that state and instead of treating it as a coherent superposition, you can replace it by an ensemble of these, like a classical ensemble of these different states, because the cross product is very small. Okay. Right. Here's another way to motivate why this is a good idea to think about classicality, and I would love to actually talk about this for hours, but I just have 1 minute. Okay, ignore these kind of things, but so when we talk about our world, we actually use a lot of conditionals, right? We say like, oh, if something happened yesterday, then tomorrow this will be the case. Or suppose that this happens, then this follows. So I don't know whether you ever thought about this, but all these conditionals, they're actually ill-defined quantum mechanically. You cannot form them. There's no way to talk about an if that condition, then this. Unless somebody really did a measurement there and said like, look, I observed the system to be there, then you can form it, right? But here within the many worlds, there's actually no primitive notion of measurement or anything. So based purely on unitary quantum mechanics, there's no way to make these statements. And this is much related actually to this famous question that Einstein asked, is the moon there when nobody looks? I don't know whether you know that question. And actually, so we use a lot of classical reasoning to describe things. For instance, like also in cosmology, right? We have a lot of classical models describing things. Not only the solar system, but I don't know what else. But why can we use that? Why can we even use classical language, classical probability theory to address problems, right? And what you will see, and I will not derive it for you, but actually, if this condition is satisfied, this basically allows you to form well-defined conditional probabilities. As long as you ask questions about, these kind of variables, x, which depend on the projectors, right? Okay. So that was the motivation, and that's the condition we will look at. Now, this condition might be satisfied or not for a quantum system. This is still completely general. So the question is, okay, when should we expect things to decohere in an isolated quantum system? And the theory we have for that is more or less the following. You take a quantum many-body system, so it has a huge Hilbert space dimension, there are many particles, It's non-integrable, and I don't want to define what this means for now. And you look at a coarse and slow observable. And then the process you will look at will actually look classical, in the sense that you could really describe it by classical stochastic process, and you can disregard one of the decoherence. Now, does anyone know who that guy is? Downstairs? Yeah.
Not numerical.
No. Okay, so this is Nico van Kampen. I don't know whether you know Van Kampen, but he was a pretty famous statistical physicist. And he said it in 1954. Okay, and I make this statement because people often say, oh, decoherence theory was invented in 75 or whatever by some paper about an open quantum system. But I think the origin goes at least back to that paper, although of course he didn't use the word decoherence, he was not talking about many worlds and history and whatever, but he makes the statement pretty clear. Now, as a way to explain this kind of thing, in case I'm not really clear what I mean by that, I have my favorite example that you all know, just a cup of hot coffee, right? If you're a statistical physicist, you would model this by saying, oh, there's a cup with this hot liquid inside and it's coupled to an outside air, basically, and all together, let's assume it's an isolated system. Then it's pretty clear this is a many-body system. It will be also non-integrable because that's what natural systems tend to be. But the point I want to make is, what does coarse and slow mean? Well, coarse means that when you drink your coffee and you basically sense its temperature, or its energy if you want, you get almost no information about the microscopic state of the system. So it's a very coarse observable, right? And what does slow mean? Well, slow means that by our experience, we know that the temperature of the coffee changes on, let's say, minutes time scale, which is many orders of magnitude larger than the time scale of individual quantum mechanical processes in the coffee, which is, I don't know, the femtosecond time scale, all right? And those observables will behave classical, according to what Van Kampen said. Now, he argued for that, and I think he has the right picture, but, well, first of all, he wasn't able to do any numerics. And second, also, there was no real analytical derivation that he has given. And a little bit my research has been to try to make up for that a little bit. So on the next slide, I will show you an analytical result, but it's not too important, but I'm very proud of it. That's why I will show it to you. And then some numerics to make it maybe more clear, okay? So what's the analytical result? And I think I try to be very quick. But here, what I look at is this overlap of two different histories where actually you start in the same state, you end in the same state, but you go through a different state in the middle, like a double slit experiment if you want. Okay. And then under the assumptions above, which you can formalize by something like tools like random matrix theory or something called the eigenstate summarization hypothesis. If you haven't heard about it, never mind. But what I show is that this overlap basically decays with 1 over the Hilbert space dimension with some exponent alpha, and that exponent is not universal. It depends on the precise model and the initial state and these things, but it's of the order 1, so typically around 1/2. Okay. And what does it mean? Well, the Hilbert space dimension scales exponentially with the number of particles in your system, right? So you have an exponential suppression of these interference effects as a function of the particle number. Okay. And as far as I know, there was no such scaling law ever reported before. And why am I proud of it? Well, if you look at the papers, you will see it's a many pages long calculation. So better don't look at the papers. So let's try to
What again?
these are Hilbert space dimension of your global isolated system.
Is the dimension of
The Hilbert space
Hilbert.
of your full isolated system. Yeah. Your universe, basically.
So in a very high dimensional space, vectors become more and more orthogonal.
Exactly, basically.
But this is true, I think, in math anyway.
No,
Infinite space, infinite dimensional space, Oh, maybe it's
No, yeah, it's not so easy, right? I mean, because in between these things, you have these unitary time propagations, and actually they change your vector, and you can find counterexamples to that. So you need, for instance, coarse and slow observables for this to be true in general. So it's not a trivial result.
yeah, I guess it's not exactly. They don't different.
Yeah. Well, but we can discuss it later on, maybe, but we also have counterexamples. Okay, but let's try to make things a little bit more tangible. And actually what we imagined in this paper was kind of a situation analogous to the copy thing. What we say is we have two systems, okay? They have certain energy eigenstates, and we couple these two systems by some random matrix and let them exchange energy. Okay. So why do we choose a random matrix? I don't know whether you're familiar with random matrix theory, but random matrix theory, basically going back to Wigner, the idea is that it mimics very well generic properties of complex quantum systems. Okay, and that's why we use it, because it's a very convenient tool. But I want to say there are many drawbacks associated with random matrices. But that's just a start. And in particular, as far as I know, also nobody really tried to compute these overlap elements in decoherent histories, really from a first principles perspective. So what do I mean by that? First principles really mean you just take the Schrödinger equation and just do brutal exact diagonalization and time evolution. No Markov assumptions, no master equations, no perturbation theory and all that, but just exact dynamics. So then we need a coarse observable. That's why you see these long lines, because we divide them, each many-body system, we lump together a few nearby energy eigenstates, right? There's some coarse notion of energy. And if you're interested in more detail, here in this paper actually we take initially a Haar random state, we just sample a random state from some microcanonical subspace at a given energy. And remember, there were times where you insert these sum over these projectors, and we choose a difference between times on a time scale where you really see non-equilibrium effect. I don't want to basically define this too precisely, but we really sample the process on time scales where things are really changing and where it has not yet equilibrated. Okay. And then what we look at, well, we take this expression where you have this overlap, we normalize by this norm, so this is always smaller than 1, and then we average over all these different x and y's. So just an overall measure of average decoherence. Okay, that's what we compute.
Still, initial and final times and final states are the same, and we change the intermediate steps, or it's an average over all possible paths.
No, so we fix, so we draw one state, fix it, we draw one random matrix coupling and fix it, and we compute everything in one run, and then you get all those psi x at once, right? You get them all at once, and for this we compute these overlap elements. So the average here does not refer, that's very important, does not refer to an average over initial state or an average over random matrix realization. Everything is one single shot you want. Okay, so what are the results? Let me try to go through them. So you have 4 pictures, and they all differ by the length of the trajectory considered. So you have 2 time steps, 3 time steps, 4 time steps, 5 time steps. Here's the Hilbert space dimension in logarithmic scale, and here's this epsilon I just introduced as average decoherence in logarithmic scale. Okay. Now, what is a single blue cross? Well, a single blue cross is, as I just explained, is a single initial state, a single random matrix Hamiltonian, and you compute the decoherence that you get. Now, the first important point you see is that actually these crosses, they cluster around the same value, so you have some kind of typicality. So it doesn't matter which random matrix you choose, it doesn't matter which initial state you choose, they all give more or less the same result. So it makes sense to make like a scaling fit through these averages, which is the red line. And then you see what we see that actually this goes off with more or less 1 over the square root of the Hilbert space dimension D. Yeah, so this is the exponent I talked about in 2 slides ago. So you really see that there is the exponential suppression of interference effects. Okay. So theory seems to work. That's the main message. If you're interested in more details, well, we checked a lot of technical stuff that's not so interesting, maybe for now. But actually, if you think about this model in some sense, if you want, what we start with is a globally timed symmetric universe with some equilibrium state. And what you see is in all these different histories, well, different histories start to develop errors of time, but still in a way that globally everything is time symmetric. So you have some error of time going forward, one going backward, they all exist in parallel. So you really, what I like, you see that, you know, you get a second law and you get maybe Boltzmann brains, all these kind of things out of this minimal model, which is quite nice.
Sorry, can I ask the question about the previous slide?
Yes.
So this epsilon is the average of some measure of decoherence between different histories.
Yes.
Are there any histories which are close together? I mean, in the sense of not. Are there any histories which are still quite coherent?
That's a very good question. For that example, not, because we also actually here showed an average, but we also checked the worst case scenario, and also in the worst case scenario, we observed similar figure. I can show you after the talk. But actually, it will start to play a very, very, very important role. What comes now? Okay. Now we come to the last part of the talk. I hope I still have a few minutes, and that's a probability problem. So what is a probability problem? Well, we said many words is only Hamiltonian and wave function, and that's it. Okay, so everything evolves actually deterministically. And the question is, how the heck do we get in this picture any kind of uncertainty, probability, or Born's rule out of it? Okay. And what I said previously with a preferred basis problem, I said, okay, there are many detailed questions open and important ones, but nobody doubts that decoherence plays an important role. I think here it's not even clear how to answer that. So nobody has an idea. I mean, well, many people have many ideas, but there's absolutely no convergence. And many people have many counter ideas. So let's make the problem clear by thinking about the structure of the multiverse in a simple, like quantum coin flip experiment. You have 2 outcomes, 0 and 1. Okay. So you start somewhere and then you measure, you get 0 and 1. And let's think about a frequency experiment where you try to infer what is the probability to get 0 or 1. So what do you do experimentally? Well, you wait and re-prepare and try to make sure that the next trial is independent of the first one. And you repeat, and then you get again 0 or 1. And this you do many times, so you get these exponentially many branches appearing, right? Now, how are these branches distributed? Well, it's always a binomial, right? So if you ask the question, how many ones do you have along one branch? Then this is always centered around L over 2, where L is the total number of repetitions in this experiment, right? Because it's basically you always have these 2 options and you just count them. So you get this binomial thing. And now you realize there's kind of a problem. Okay. Why? Well, according to this picture, and remember this becomes like super steep and narrow in the limit where L becomes large. In almost all universes, you will see sequences where 50% of with 50% 1 and 50% 0, like 50-50. But suppose you prepare a state, a superposition, where according to Born's rule, the probability say of 0 is 1/4, and the probability of 1 is 3/4. Right? Then if you would apply Born's rule to this experiment, you get such a distribution. Okay. So it's very different from that one. So the question arises, if you are in a multiverse, how can it be that we live on a branch where we see Born's rule and not just 50-50 always? Okay. So that's a probability problem. Does it make sense, this problem? So basically, the basic idea is, again, within many worlds, there's no distinction. There's no Born rule a priori, there's just unitary evolving wave function. But each time there's just a splitting, you have one branch with a 0, one branch with a 1. So it's always 1, 1, 1, 1. If you count, then you will see that if you take a typical branch here, it's just 50% 1, 50% 0 with some small fluctuation. So if you do this frequency experiment and you record 1, 0, 0, 1, 1, 1, you say, it's 50-50. That was a 50-50 superposition. But what we believe, according to, say, Copenhagen interpretation, is that if you have a superposition which is not 50-50, you should actually get, maybe such a distribution out at the end. But within many worlds, you always have that. It doesn't care about the coefficient in front. Okay, that's a problem you have to solve. Okay. Did people solve it? Well, there's a long list of proposed derivations. I will not go through them, actually. I think they are all nice. They have their merits. But, well, there are a couple of problems. So first of all, you can see that even the proponents of many worlds who propose certain solutions to it don't agree on what is the solution. There's already a remarkable discrepancy between them. Then, what I haven't written down here is all the counter arguments that you can find against these things. And I think there are two main problems with it. So first of all, remember, many worlds says everything is just Hamiltonian wave function, that's it. And actually, most of them, if not all, actually add little additional metaphysical postulates to it. So they're actually already out of Everett's many worlds interpretation by adding some additional interpretational elements. But then, still, even if you accept there's some sort of a Born rule, I think that problem simply remains. And why does it remain? I don't know whether you ever looked at the famous paper from Everett or from the 50s, the Review of Modern Physics, where he introduces that. So the title of this paper is Relative State Formulation of Quantum Mechanics. So actually, he was not calling it the many worlds interpretation. Why was he calling it relative state formulation? Because he thought, well, you have all these branches, but you self-locate yourself on one branch, and everything what is to you accessible is just the branch which is compatible with your observation. You don't see the other branches. And actually also, all what you see is just, say, your state, but the coefficient in front of the wave function, you don't know it. You cannot know it. And you don't know whether the other branches and what kind of coefficient they have. But these coefficients are important for Born's rule somehow. But if for you on your branch, the coefficients don't play any role, then you kind of still are left with this problem. You just split in most worlds will always give you 50-50 probabilities. Okay. Is there a way to solve that problem? Well, I don't know. But it really bothered me, and I thought a lot about it. And I thought, okay, so you might not like the frequency interpretation of probabilities. I don't know what your favorite stand is on probability. But in an experiment, it's pretty clear that we confirm probabilities by a frequency experiment, right? We just do something very often, and then so for instance, now in quantum technologies, if they measure a single qubit and they do what they call state tomography, they re-prepare the thing roughly 100,000 times and measure it again and again and again. And at the end, they construct statistics and say, now it's enough, the qubit is in the state. Okay. So I thought, okay, maybe we should try to do this with our simple random matrix toy model and go to very large L. Okay, and see what can come out. So that's the idea. Okay, we should look really at very long sequences. That's my most recent work here. Now, you actually see one problem. So remember, you had all these projectors which you insert, and you get these branching. So if you go actually to very large L, you have exponentially many components in your wave function. So already for L around 20, you cannot even store this anymore on a normal computer. But, and here we had some nice idea to make things simpler. So first of all, instead of having what we had before, which is two coupled systems and everything, he takes a simple case, just binary 0, 1. Okay, these are two outcomes. There are two projectors dividing our Hilbert space. And whatever these projectors look like, you can always then write down the Hamiltonian in that basis. So there's a block diagonal form. And what we use is we take those to be simple diagonal matrices, and these off-diagonal ones are again random matrix blocks. Okay, just to mimic again some complex quantum system where two parts are kind of interacting. And now the trick we do is the following. So instead of considering those for which we have exponentially many, we say actually what we just asked about this experiment is what is the frequency of ones or zeros in my long trial. So actually, we define those states where you add up all the states which have the same number of ones, right? So x1 to xl goes from 0 to 1. So we all put them in one state, which we label psi of n. And now you have actually only L plus 1, many of them. So the exponential complexity is reduced to linear complexity, and now we can go to large L. Okay. And now on the next, what we will look at is again some decoherence quantifier. This is actually the same as before, but now we don't average, but now we take rather maximum. We say like, okay, suppose I'm on a branch where I have n times 1. Then I might wonder how well am I decohered from all the other branches which measure a different relative frequency. So we maximize over all other ones, and we ask, okay, am I decohered from all the rest? Or is there maybe some branch with which I'm strongly interfering? Okay. So to wrap up the picture, we are here, we go to large L, okay, and we have all these different branches. And actually here what I've got is if you would follow one branch, then what you would see along this branch is something like that. So you actually, well, we start, we don't do anything, and then you would get a 1. So your probability for this projector goes up to 1. And you would reflect back to equilibrium, then you saw a 0, and another 0, and then a 1 again, okay? And now I make this point because now we choose a time difference here to be of the order of the equilibration time. Why do we do that? Well, because in the frequency experiment, you want to ensure that different trials are all independent. So this we do here in our toy model by just waiting long enough that things basically equilibrate from a macroscopic point of view and look, give you identical statistics. And then in this example, the probability to get outcome 1, and this is statistical mechanics, that's basically the expectation value in the microcanonical ensemble, if you want. It's just the trace of this projector divided by b. So in this example here, you get 50-50, so the projector was actually projecting on half of the Hilbert space, and pi 0 would be the other half. Okay, so it's just an equation you will use. You just have to believe it now. Okay. So let's study the decoherence along this tree. And the picture is not so interesting now, but I just want to explain what we plot. And then I go to the interesting picture. We plot 3 things. So here you see, so first of all, we look at the short, say, trajectory, 25 repetitions of the experiment. And here is n minus average n, just to normalize things. So this is how many ones you see in your trial. And then the blue circles give you just decoherence that I just introduced. This kind of maximization thing telling you how much am I decoherent from all the rest. Then the purple line, that will be the standard probability you get by applying Born's rule to an independent experiment. And this thing is, the actual Born's rule if you don't assume independence between experiments, but just the full multi-time quantum joint probability. And using a very small result space with 250, you see actually the black stars, they're not at all matching the purple line. So, there's a strong finite side effect, not really sampling any kind of independent equilibrated process. But things get much better if you crank up the result space dimension, all right? Now you suddenly see that the stars are pretty close to the predictions of independent experiments. And what you also see, what I actually showed you before, the scaling law, the decoherence goes down pretty dramatically because you have a much larger result space. Okay. Well, that's 25. 25 is not yet a super long sequence. As I told you, like in labs, I do hundreds, thousands of repetitions. So we went up to 250. Okay. Again, for the small result space dimension. And what you can see now is already kind of a nice structure appearing in the decoherence. So you suddenly see that in the middle, where you would expect most probability to be, you also have the strongest form of decoherence. Whereas if you go away from it, you get super strong coherence. Okay, so this goes up to 1, and remember, 1 is the maximum value you can get. You cannot be more coherent than that. Okay. So already the small system, you see kind of things decohere where you sample the right probabilities. More or less. Well, look at this. So now what you see is, this large system, the actual probabilities almost perfectly match the prediction of an independent frequency trial, which is a binomial. And you see, basically you're perfectly decohered along all branches of Born's rule, and the rest is super strongly coherent. Okay. Now, you might say, okay, might look nice, but actually here, you're still in the 50-50 case, so where the projectors on these two different subspaces have the same dimension, are equally large. And if you remember, for 50-50, that's exactly the only case where you don't have any problems in many worlds. Because 50-50 you get for free. What we did is, okay, we changed the size of the projectors and said, okay, one is 80% of the result space and the other is 20%. So we have basically different probability P1 here, which would be then 0.8. And what you get, and I show you only basically the lower right picture, is that. Okay. So what do you see? So everything is shifted, of course, because now you have 80% probability to tier 1. Here, the orange squared is the decoherence for the small Hilbert space dimension, the blue circle is the big Hilbert space dimension. And here, this is the black stars are only for the large Hilbert space. So you can see that Born's rule perfectly matches the independent frequency trial interpretation. And you still see that you basically, the classical trajectories, where you have really observers who perceive a classical reality, are exactly centered around the Born's rule probability. Whereas if you go away from it, it again shoots up pretty dramatically to values where you can't have any classical observers anymore. Okay, so that's what we see. That's evidence. Purely numerical and just the toy model, but at least there's no other approximation, right? Everything is just unitary time evolution, exact diagonalization.
So I want to understand. So there are two kind of dimensions here. The dimension of the Hilbert space and the length of the L, which
Yes.
are layers. And each time you increase those two numbers, you get more coherent with the classical picture.
Yes.
So it's just a matter of high dimension. Or is it?
No, so here what you see, so here I increase the Hilbert space dimension, and if L is small, you still have this picture where basically everything can happen and all branches decohere. And you also see branches where you have 25, like you flip your coin 25 times and just get heads all the time.
But D is large.
But D is already large, yeah. So you see already, you sample well the probability you would expect to sample, right? But the new point is if you go to large L, you see it's no longer true that all branches decohere, but only a very particular subset decoheres. The remaining ones are actually like maximally interfering. Okay. So, oops, that's the wrong direction. Let me just wrap up. I tried to have a slide where kind of everything is on it. So we start from this kind of picture. This stuff, this gives you classical results. Actually, I put non-integrable in brackets because it's not fully clear whether you need non-integrability or not. And then you look at decoherence. And now there are two different ways to look at decoherence. Mostly look at environmentally induced decoherence. That's the standard approach, where you actually just consider the density matrix of an open system. Now remember, the density matrix is a one-time object. Actually, it's just information about an observable at a single time. So in some sense, in this number of trials picture L, you're here in the one-time regime. Okay. And now what most people had in mind, I guess, without even actually admitting it, is some kind of Markovian idea. So they said, we understood environmentally induced decoherence for a single time. So, if I do an experiment and I look at multi-time propagators or correlations, everything will still be decoherent. And the picture you end up with is with what I call naive branch realism. So you really have this picture, everything that can happen does happen on some branch, and each branch supports a classical observer. Okay. And this is really a standard picture that has been used by proponents and opponents of the many worlds interpretation. They never question that. Most of them are not even saying that this is an assumption. They just say, everything happens anywhere, and now let's discuss it. Okay. Now, in my recent work, I took another route. I started from the decoherent histories, which, as I said, are completely compatible with that, so they're not in conflict. But they kind of emphasize a different angle. And in particular, I think they're more natural to study multi-time properties. And then, when you remain in this small, low L limit, you have really the situation, everything everywhere all at once. That's what we basically showed. I don't know whether you have seen the Hollywood movie from 2 years ago, which has the same title. And this was basically in that paper we studied that, and you get the scaling laws and these kind of things. But then if you go to large L, it suddenly is no longer true that everything everywhere all at once happens. But there are just a few branches that actually remain in the sense of, let's say, remain decoherent. Okay. So I tried to sketch this here, where the black ones are the decoherent ones, and all the gray ones are actually strongly interferent. Okay. So you really get a non-trivial emergent structure in your many worlds tree. And maybe there's absolutely no clue whether this is true or not. Maybe that's related to Born's rule. We cannot say, it's just a too simple model. But I think at least we have demonstrated that the many worlds tree is not as structureless as everybody thought. And yeah, this was in this last paper, and maybe to finish, I could start to write a blog. If you're interested, you can take a look at that. And with this, I thank you for your attention, and I'm sorry if it took too long.
It's fine. So
You want to have questions? Or more questions? I will start in the picture of this emergent structure. It reminds me of what happens in disordered systems.
Mhm.
You can have exactly the same disordered systems. So suppose you don't have anything quantum here. Just you do a branching process with some P and Q probabilities right down on left. In the end, there is just a few states. Actually, there's a ground state that is the one that where the system localizes. If you just do some branching, a few branches, you have all your possibilities remain. Still have some certain probability, but as you go farther and farther inside and branching, there's just one of the solutions is not only the one that minimizes the energy, the cost of that branch, but also is the only one that is actually observable because it's exponentially suppressing the probability of the rest.
Okay.
So it reminds me a lot of what happens in branching, well, in the direct polymer problem, for instance.
Okay. Well, that's interesting.
It's nothing quantum. It's just it's related with the properties of the random matrix.
Okay.
It's a random matrix.
Yeah, I mean, this might also be here related. We're still looking for a good, simple explanation, which is intuitive. Also, maybe there's none because it's a complicated many-body quantum thing. But yeah, I mean, this analogy could be interesting to explore.
At the end of your section on the preferred basis problem, you mentioned something about hours of time coming up to branch history. Would you mind just explaining that?
Yes,
a little bit more?
I don't mind. I mean, maybe that's best explained here. So, yeah. So we look at a very simple situation, obviously. We have these two coupled systems, and you constrain them, say, in 3 energy states, okay? And what I said is like we restrict things to some microcanonical energy shell to make the optimal use of numerical resources. And what we actually do is we consider a total energy, which is say the sum of these two middle energies. And then what remains within this model are only 3 different configurations. So either your system is here, or it's here, or here. They all add up to the same global energy, right? And of course, in a more realistic model, you would have, more there, but we just consider these basically 3. So our projectors have just 3 values. So either even energies, or one system has more than the other, or the other way around. Okay. Now, what do we mean by emergent errors of time? Well, the equilibrium subspace, where you would naturally spend most of the time, is the one with even energies, because we actually consider 2 equal size systems, okay? But then you start with this completely random state, and you look at your trajectories, and you will see that your status overlap with, making the transition from here to that state. So suddenly, actually, energy flows, say, against the spontaneous creation of a gradient. Okay. And that is what we say, okay, this would be like an inverted error of time. You start with equilibrium, and suddenly it's non-equilibrium. But of course, there are also branches where you're somewhere here, and you equilibrate again. That would be for us a forward error of time thing. Okay. So basically, when we study this kind of, here we have it. These kind of things, we see different branches, and sometimes basically they go with this conventional error of time, sometimes against it, or sometimes nothing at all interesting happens. So according to this, we label these different things, and they all happen in that superposition. And what we see and what should be the case, because first of all, you have time versus symmetry in the dynamics, right? But then also we start from an equilibrium state. That's why we say we sample randomly from mechanical state. So we are not putting a low entropy initial condition. The resulting picture we should get out should always have as many forward as backward errors of times. And this is also what we confirm, and actually have an additional slide. That's this one. So this picture where you have these three states and we label according to the error of time, and the distribution of errors of time is always perfectly symmetric. So this is, I think, backward, this is forward, and this is no error of time, and you see it. Everything remains time inversely symmetric, but within one branch, you might perceive an error of time. That's I think it's quite funny. I mean,
But is the suggestion from those plots that it would be unlikely to find yourself in a branch which has an arrow going in a direction? Or not?
yeah, so basically it's unlikely, so it's more likely that you're on a branch with say a boring equilibrium branch, because we don't put a non-equilibrium initial condition, but we start from an equilibrium condition. And that's related to this Boltzmann-Brain paradox, right? That I don't know whether you know this, but you know, Boltzmann, this idea that error of time comes from the universe being an equilibrium, and it just spontaneously fluctuated out of equilibrium, and now we're just really fluctuating back to equilibrium. But according to this argument, it's much more likely that just single brain with the impression of living in a universe like us, like we experience, fluctuates out of it, than the entire universe itself. And this is kind of what you see here. So if we would go to even larger spaces, I think this would become even more suppressed, and you would say, okay, you get all these errors of time, it's nice, but they're very low probability. Okay, yeah.
You said that was just because you started the system already in an equilibrium configuration.
Yes, if you would start with another configuration, you could get an asymmetric picture out because you put an asymmetric boundary condition. Yeah.
No more questions. I think we take a quick.
I remember I was before.
Yeah, as it gets more and more leverage, it takes over.
Yeah, not that I-
Well,